Newton's second law of motion. We recall that in second law of motion, we have that F vector is equals to m multiplied by a vector, and then by defining p vector as momentum, which equals to m multiplied by v vector, that means F vector is equals to the first derivative of p vector with respect to time for first derivative of m or mass is equals to 0, which we know that this is a conserved quantity. So that means we will have two definitions, which is for acceleration multiplied by m is acceleration definition, and by first derivative of p vector is momentum definition. But in this video, we will focus on m multiplied by a vector. So now if a vector is non-zero vector, we will have the expansion just like before. And as example, I will give you in 2D coordinate, which those is Cartesian and polar for only this video. In two-dimensional Cartesian coordinate, we will have a vector as before, and now the basis is collected a set of bases which is as x hat and y hat. And notice that this is orthonormal basis and a constant basis. So that means we will have this result which there is no derivative with respect to time for basis because it is a constant vector, which in previous video for a vector is equals to 0 vector, this will lead us to momentum conservation, or specifically as linear momentum conservation p vector. And next, in two-dimensional polar coordinate, we will have expansion of a vector as before, and now the set of bases is r hat and v hat, which both is orthonormal each other. In this coordinate system, we know that both r hat and v hat may be not constant with respect to time. So we will have this expansion, which is position vector, can be simplified as r multiplied by r hat, as we seen in coordinate system video. In coordinate system video, we recall that the relation between polar and Cartesian in two dimensions as these two, which means that the first derivative of r hat will equal to this, and the second derivative one just like this two, and by simplifying as the definition of r hat and v hat, we will have simple term by substitution, as this part is for v hat, this part for r hat, and this term too as v hat, and so on. By collecting each result, we will have this, and by using force vector is equals to m multiplied by a vector, we will have two special conditions. First, for first derivative of r is equals to 0, then the radial part of the force will equals to minus m multiplied by r and multiplied again by the first derivative of v squared. And this result was known as centripetal force, which the first derivative of v known as angular frequency. And next, for angular part force is equals to 0, that means it will have this term as 0. So by multiplying both sides by r, we will get this by using product rule, and by defining L equals to m multiplied by r squared multiplied again by angular frequency, we will get L as angular momentum. So by this first derivative is equals to 0 equation told you about conservation of angular momentum. So these two special characteristics about why we choose polar coordinate for simplifying rotational motion along polar two-dimensional plane. And for addition, at last part, I will introduce the three-dimensional cylindrical coordinate, which the set of bases is polar coordinate as before, but now we have z vector as part of Cartesian coordinate. So if we redraw the coordinate system, we will get the xy plane ruled by r hat and v hat, and now we have z hat as usual in Cartesian coordinate. Then define tau vector as r vector cross I vector, which known as torque. And by this system, we interest for pure v hat part force, so f dot r hat equals to f dot z hat is equals to 0. So that means if we take tau vector by definition, we will get this long equation, and by the end we will have the first derivative of L vector. And the interesting part, the result of tau vector is equal to the first derivative of angular momentum vector has analogical relation to force vector equals to the first derivative of momentum vector, which for F vector related to linear momentum, but for tau vector relate to angular momentum. That's how motion between linear and angular or translation and rotation related. So that's how Newton's law of motion told you about motion. In this video, we know that the motion not only just for straight line but also rotational, but also any possible motion that can be described as first law, second law, and third law, Newton's law of motion. I think that's it. Don't forget to share, like, and subscribe, and see you later.